Greetings. We're going to start off with a little trivia. One of the longest words in the English language, or I guess world because it's across languages, is the name for the largest known protein with 169,723 carbons. And once again, tens of thousands of H's, 270,000 and some odd H's, nitrogen, oxygen, sulfur. Look at how many isomers would probably be possible there. So it's actually important to get the name right so you're not mistaking it for another compound. Of course, it has its nickname, Tintin, but for a good reason, because it takes 3.5 hours to read the whole name. And it starts with methionine, alanine, threonine, serine, arginine, glycol. And don't worry, I'm not going to read it. But what I want you to kind of take away from that is we need names to distinguish between isomers. So you can guess what we're talking about today. We're going to work on alkanes, much simpler than proteins. Don't worry, you'll get there someday, biochem. But got to start somewhere with organic naming, and alkanes are the right place to start because then they don't have all those functional groups that you have to name in addition. So today's focus is going to be on introduction to nomenclature and starting with alkanes and the rules that we follow. And you might have listened to a lot of ills at the end, and we've alluded to that. That's a sign that it's a branch as opposed to part of the main chain. So that's what we call a substituent. So we'll get to the ill versus the one that has a proper suffix and work that all out in this lecture. So let's get started. All right. Just recall, the reason we're doing alkanes first is because, once again, they're simpler. They're saturated. What makes it an alkane? They're saturated hydrocarbons. Saturated hydrocarbons. What does that mean? Saturated means there are as many H's as possible per C. So if something's saturated with something, it means it's as full as possible of that thing. So if it's saturated with hydrogen, as many H's as possible, provided it's governed by carbon's valency on each C. So for example, we have propane. We know that when we draw propane, if it's saturated, which the name implies that it is, because it's an alkane name, those are the correct number of carbons for propane, right? And hydrogens. C3, H, 8. All right. So the formula is predictable for an alkane that's a saturated hydrocarbon. For every n C's, there are 2n plus 2 H's. So saturated hydrocarbons follow that pattern. That's actually very useful. We use that to sometimes decipher other structural hints later when we're trying to solve for like a mystery structure. So if it satisfies that formula, you have an alkane, saturated hydrocarbon. So in other words, that carbon's not attached to other atoms. It doesn't have pi bonds, doesn't have rings even. So because you can have an alkane that's a ring. So generally a formula for an alkane that is saturated. Okay. All right, so our goal is to get into naming, and we did a little bit of this just so we could talk about some simple molecules, but we're going to once again use these prefixes, so you'll want to know those to indicate the number of carbons. And when we're going to name an alkane molecule by itself, we'll use the prefix, and then because it's an alkane, it keeps the suffix ane. If we're going to call it a substituent, then it gets this YL suffix. So for example, here's a table. Methane is a molecule, and we'll write the name next to it. Methane is a molecule, but if you're talking about a substituent with only one carbon and then the maxed out H is attached, notice we lose an H to get from methane to methyl. And that's because this bond goes to, we could draw a little squiggly line, like an R group of some sort, right? R, or put a squiggly line to indicate that it's coming off of some bigger chain. So when that's the case, when one carbon comes off as a branch, like as a substituent, then that is called a methyl group. The abbreviation for methyl, because they are so common, we use abbreviations for them, Me. So increase that to 2 carbons, that molecule would be ethane, and let's work our way down this time. Oh, I almost said propane because I was at being a robot, but look, count your carbons. 1, 2, 3, 4. Oh, I didn't draw propane. Oh, I drew propane up above. Probably why I did that. So butane. So let's do the next one. Let's count them all. 1, 2, 3, 4, 5, 6. Look at that, we skipped the hexane. Okay, so what would we name that bottom one? Nonane would be correct if that's what you guessed. All right, so then to name their analogous substituents, ethane, if it was a substituent, would be ethyl. So we don't say we have an ethane substituent. Ethane's a molecule. Once you have that suffix there, you've wrapped it up and it's full of its hydrogens. Butane, if it's hanging off of something bigger that is not necessarily defined, or we just want to focus on the group that's coming off with 4 carbons, we call it butyl. And likewise with this hexyl, and of course nonyl. So you want to be able to do that with those 1 through 10 prefixes. So what's the pattern you might see as we increase these carbons? CH3, CH2, CH3, CH2, 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 CH3, CH2, 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 then finally CH3. So in other words, an unbranched alkane, if it's just the molecule by itself instead of an alkyl group, you're going to start with a CH3, and then I'll have all these CH2s in the middle, and then end with the CH3. And so CH2, let's put N, because it's just depends on how many you need to make that size molecule. So that's your general pattern of an alkane that's unbranched. All those CH2s in the middle, flanked by CH3s at the end. Okay, so just remember though, now that we're naming bigger things, isomers come into play. So we have to, when the goal with names is to make sure it only describes one of the many possible isomers. That's the problem with the formula. Formulas do not describe all of the possible isomers, right? So for example, if I said, okay, butane has lots of isomers, let's discuss them. Okay, so notice I've put this little hexagonal graph paper in there. It's optional, you could find free printables on it, but while you're getting used to drawing alkanes and lots of chains, I thought it'd be useful to kind of follow the grid to keep our bond angles nice and tidy. So let's see, butane, 4 carbons. The most straightforward one to always start with is the straight one, the linear. So no branching, in other words. So that would just be, I already have 2 carbons there, 3, 4. And always count 1, 2, 3, 4. So that would be N-butane, normal butane, okay? Now, that's not the only way I can arrange 4 carbons. They don't have to all be in a line. And remember, butane, let's say C4, what would the formula be? C4, H2N plus 2, H10. So let's do that one. Okay, what else could I do with butane? Well, I could take off one of these methyls. So let's see if I have something like this one. So I could take off the methyl at the end here and put it somewhere else, right? I could put it on number 2. So I'd erase that and then move it here. If I put it at the end, I get N-butane back. So my only choice to really add any variability is to put it there. So let's draw that one in the middle. Oops, I drew 4 carbons again. Can't do 4 carbons in a row. So in other words, I have a propane parent, but because I'm going to make a butane total with 4 carbons, it's going to be branched. Okay, let's name that one. Propane's the parent because I have 3 carbons in a sequence. I don't have 4 in a row anymore. So propane's the parent. But something's happening at carbon 2. It's got what on it? A methyl. So we'd say 2-methyl propane. Okay, so this satisfies, if you fill in all the H's, these are both isomers of C4H10. Can I make a ring? Sure, I can actually make a ring, but then let's fill in all the H's that are on a ring. 4 carbons would make that square shape. Ooh, look at that. 4 carbons, 2 hydrogens each, means C4H8. What happened? That does not match our formula. So imagine taking this carbon and attaching it to this carbon. So if we numbered this, 1, 2, 3, 4. In order to make the bond between 1 and 4, 2 H's have to come off. So this is a CH3. This has already got 4 bonds. This already has 4 bonds. So if you're going to make a 5th bond, that's not allowed. So you take an H off of here, an H off of here, then you connect it, hence the lower value of H's in the formula. This is not fully saturated, so it is not an isomer. So don't worry about rings when you're talking about isomers that describe a saturated alkane. So notice how the formula I gave you describes C4H10, a fully saturated alkane. It's CnH2n plus 2. This is not CnH2n plus 2. It's actually CnH2n. Okay, so, but this brings up an interesting question. If I said, hey, I've got butane over there. Well, it turns out there's 2 butane C4H10s, right? If I said, oh, I've got C4H10, you say, is it butane? Well, which one is it, right? So we have to make, that's why we need the names. So C4H10 told us the formula and how many atoms, but the N-butane versus the 2-methylpropane has a totally different parent name, lets us know we're talking about 2 different molecules that have the same formula. So naming is really helpful when we are trying to distinguish between isomers. So some rules I followed that we've been kind of doing all along, but let's make them official now. The rules that we use are very systematic, and they're established by what's called the International Union of Pure and Applied, let me bring this over here because I can't reach it, chemistry, aka IUPAC. So the IUPAC has come up with these system of rules so that worldwide, when we describe a molecule, if we use this system to name it, the other person will draw the same molecule. They won't draw an isomer on accident. That's the goal. Okay, so here's a checklist you might want to just kind of rewrite every time you're naming. And I've actually made this more detailed than we need just yet, because when we do alkanes, some of these things don't apply. But this is a page you might want to bookmark and come back to throughout the chapter as we're naming. Because every time we cover a new functional group, we'll learn how to name a molecule that includes that functional group. But it'll always start with the same first step. Find the parent chain. I suggest going ahead and circling it. That's the longest continuous chain of carbon atoms you could find. Then you have to number them. And you can sometimes number from one direction or another. So we'll do some examples like that. But you want to make sure your substituents get the lower numbers. That way we're all consistent. Then if you have any functional groups, you're going to have to use a chart to find the highest priority one, unless you memorize the chart, which I don't require, but it's something you'll want to bookmark and look at the chart. So identify the highest priority functional group, and there's a table that's to follow. This determines what suffix you use. So you might have noticed we have ethane, we have ethanol. That's a new suffix. New suffix comes from the alcohol. Because the OH is the highest priority group, it got the suffix. Okay, so you actually have been doing a little bit of that without realizing it. If alkenes or alkynes are present, then they could be the suffix. So we might have hexene or hexine. But if you have other functional groups that, you know, win, if you will, in terms of priority over them, then they actually become infixes. They're in the middle of the word. And when we get to alkenes, we'll do that. Don't worry about it now. Okay, remaining functional groups are named as prefixes in A, B, C order. And so that's if you have lots of things. What if you have an ethyl, a methyl, a propyl attached? You name them in ABC order. So you rearrange them how you name them, not by numerical order, because those were the two options that usually come up. It's not numerical order, it's ABC order. Okay, so these final touches, cyclo is the only thing we're going to cover in this section, but when we learn stereochemistry, we'll make sure we have the R and S designation. When we do alkenes, we'll make sure we have the E and Z, and N for amines, but that's a ways off, okay? So focus on just making sure you know if it's cyclic or not, and don't forget to include the cyclo. Okay, so we've actually already named the butane. I did that with you. I'm going to try to do a harder one with you, though, because I think that'll make it a little more... a good one to practice after this, if you want to pause, is the 5 isomers of hexane. You can look them up and confirm that you did it right, but this is a good exercise to do on your own. If you're feeling a little shaky, then move on to this one with me. Okay, I'm going to do some branched ones with you because that will increase our complexity so that we can understand this. All right, so here's an alkane you could be asked to name. You want to take a minute and try?
Shirley, Bo Burley, Banana, Pineapple, Burley, Fee, Fine, Mo Merly, Shirley.
Okay, let's start with step 1. Who was the parent? Did you get a hex parent, a hexane parent? I mean, it is ane because it's an alkane. So if you got hexane, you're wrong. Let's number it. I say, well, I like the way this one looks. 1, 2, 3, 4, 5, 6. That's not the longest chain of carbon atoms. We can get longer than that. Alkanes are often drawn like this to make it easier on the eyes, but they can wrap here. This is a chain, that's a chain right here. So 1, 2, 3, 4, 5, 6, 7. Or 1, 2, 3, 4, 5, 6, 7. Or 1, 2, 3, 4, 5, 6, 7. So since I have 1, 2 or 1, 2 and have this 3, numbering this way is kind of equivalent no matter which branch I start from. So I'm just going to pick one and number. Let's go ahead and do it in red. 1, 2, 3, 4, 5, 6, 7. Or I could number the reverse way. 1, 2, 3, 4, 5, 6, 7. Okay, so the blue path is out. 7 wins. So our parent name is heptane. Now, which one do we pick? That comes from this answer. We want the lowest number for all substituents. And I'm going to add that higher priority substituents need to have the lowest numbers. So for example, the reason ethanol even got that suffix "all" is because OH has the highest priority in that whole molecule. But what about when we're having alkane? This doesn't always come up, but the fact that we have 2 ways to get heptane, we have to decide which path was better, the green or the red. So let's just make a list of what the green, so in green, I'm going to list my substituents and their number. So notice I'm going to go through the sequence 1, 2, carbon 1, 2, 3. Oh, I have a substituent before I go to 4. What is that substituent? That's a methyl. So it's going to be a 3-methyl. And keep going. 4, nothing, no other than H's. 5, 6. Oh, at 5 I had a substituent. That's 2 carbons. That's an ethyl. So using the green path, we have an ethyl on 5. And then I finally get to 7. Let's do the red path. Carbon 1, carbon 2, carbon 3 has the ethyl. So 3-ethyl. Carbon 4, carbon 5 has the methyl. So we're comparing those two. Usually the numbers are different, and if the numbers are different, we pick the smallest number that will go to our substituents. However, since they're the same, we want to pick the numbers that would allow us, no, but the numbers are the same, but the substituents aren't. Methyl on 3 versus ethyl on 3. So you might have to ask yourself, what's the higher priority carbon? So it turns out that ethyl, because it's bigger, it's a bigger group, it's attached to another carbon instead of another H, has higher priority than a single methyl alone. So in other words, if you look at the immediate attachment to the methyl, so notice the methyl has only H's attached to that carbon, to carbon 3 or 5. Whereas carbon 3 or 5 here has a CH2, but then we get a CH3 attached. So having the bigger group gives it higher priority. So this is the higher priority group, so we're going to give that the lowest number. Of the two choices were 3-methyl or 3-ethyl. We're going to let ethyl have the 3. Ethyl higher priority than methyl. By the way, the abbreviation for ethyl is ET. Little e, capital E, little t. Why don't we add some more abbreviations here? I'm going to go back. That reminded me, I think I want to introduce those now. So sometimes it makes your life easier to write those, and you'll see soon. Butyl, BU, and that's about as far as we'll go with that. Okay, so fill those in. Ethyl, ET, butyl, BU, methyl, ME. Propyl also has one, PR for propyl. So you might see like PROH for propyl alcohol or propanol. Okay, let's go back. So that can be a doozy, right? So we learned a couple things from that. One, numbering matters in order to find the parent chain. So the parent chain is the longest number of carbon atoms, no matter what the conformation is. But then not only then sometimes once you find the parent chain, you have to establish numbering, and you might get different answers numbering from one end versus the other. So then that's when priority comes into play. Okay, let's do this again. Let's name, but now we're going to have a halogen. And halogens are named with the halogen, so haloalkane. So this is going to be a if we had a simple thing like bromobutane, for example, that would be butane, and take off one of the H's and put on the Br. But where does the Br go? We could have 1 bromobutane, 2 bromobutane, or back to same 2 bromobutane, right? So we're going to have this alkane is going to be bromo something something ane, okay? So we're still going to do step 1, find the parent chain. Tell me what you get. I'm not going to belabor that one. You can pause because I'm giving you the answer right now. Here I go. Spoiler alert, right? Hexane. So you have to number the longest continuous carbon chain. 1, 2, 3, 4, 5, 6. Now it didn't matter if I picked that as 6 or that. This is just a convention, these are equivalent, in other words, it's symmetric right there. These can rotate around and these trade places. So either one of those is fine. But 6 is the longest I could get. But I could number in that direction. So now that we know it's 6, it's hexane, we're going to figure out the numbering of the substituents. 1, 2, 3, 4, 5, 6. Okay, so what path are we going to use? The red or the blue? Well, think about what we get. With red, we get a 2-methyl. That's where one substituent is. A 3-methyl. And a 6-bromo. Whereas in the blue scenario, we get a 1-bromo. We get a 4-methyl. And we get a 5-methyl. Who has the smaller assortment of numbers? Blue. Who lets the highest priority group, which is always never an H? So bromine, something other than carbon or H. Bromine has higher priority than anything else. So that gets number 1. So that needs the lowest number, in other words. So you want to have the lowest number to the highest priority group, and then if you still have choices, you want to have the lowest selection of numbers for the other substituents. So it's really all agreeing on the same side. There's nothing even considered blue is the only way. Okay, helps that I wrote that name in blue because now we can just add to it. So you could call this 1-bromo, but most people won't. The 1 is often implied, but we can. It's not wrong to have too much information. So I'm gonna put it way out here because I have more stuff to add. 1-bromo. We have a methyl at, so I did that. We have a methyl at 4 and 5. We have 2 methyls. So I actually need to say there's 2 methyls. Instead of saying 1-bromo, 4-methyl, 5-methyl hexane, I can conveniently combine them to say dimethyl. Di meaning 2. So we use the di, tri, tetra to help us remember. You might remember that from old general chemistry nomenclature. Whether we have 2 attached, 3 attached, or 4 of that same thing attached. So since we have 2 methyls, we are going to use dimethyl. So, but we still have to remember where they're at. All right. So 4, 5, and then we use a dash to kind of separate it. That makes it cleaner. So between the numbers and the letters, dimethyl. Oh, look at that, just worked out. I wrote that just in time to get to hexane. Sometimes I get a little too stretched out there. All right. Now I'm going to ask you, some of you, if you name this without me, you would get 1-bromo because that's the highest group. That needs to be 1. But you might have put the 4,5-dimethyl in front. Okay, so the rule is, at least the IUPAC standards are very detailed. You can get really, there's people that really love to get into nitty-gritty rules of this. And we draw a line in the sand eventually, but right now we're not close to it. So you need to be able to not only recognize which ones, how they're numbered, but also which one of these is correct. And one of the rules is that the substituents go in ABC order, not numerical order. It turns out that when we do it this way, it's both numerical and ABC order. That's just a coincidence. It doesn't have to be numerical order. So it's ABC order. B comes before the methyl. Okay, so we're going to put those in. Bromine comes first, and B comes first in the alphabet. Oops, I meant to do a red line. So not ABC order for substituents. Substituents. All right, so another lesson to take away. When functional groups are present, the carbon with the highest priority for functional group, we saw with the bromo, gets the lowest number possible. Okay, throughout the class, I would bookmark this page. Like if you've printed out this reader, put a sticky here, fold it over, whatever you want to do. We're going to do lots of functional group naming. We're leveling it kind of little by little. But if we had like a 4-carbon chain that was a carboxylic acid, that's the highest priority it could get. That one would win. That would be the suffix. So if we had, for example, an alcohol and a carboxylic acid, how do we know what the suffix is? The highest one at the top wins. So then it would end in oic acid. So we'd have like 2 hydroxy for the alcohol prefix, butanoic acid. Okay, so notice that the alcohol is usually the, where is alcohol in here? Is usually the suffix, but if there has any of these groups above it, we say hydroxy at that position, the OH group. Notice alkanes are way down here, right? Okay, so even halogens don't get a special suffix. They're below alkanes, but they are still considered higher priority groups in terms of carbons versus hydrogens. But for deciding how the suffix goes, you still get a name. So whatever the halogen name is. So halo means that you're going to replace the chlorine with chloro. So chloro hexane, for example, bromobutane, iodopentane, right? So that's how you use that. So right now we're just doing alkanes and alkyl halides together. And so those are the kinds you have to name. You're not going to have to name all the others necessarily. Yeah.
Lincoln, Lincoln, Lincoln.